I welcome all of you to the class. As far as today's class is concerned, in today's class, we'll be trying to understand how to make use of the equations that we derived in the previous classes about the deflection of the beams. Okay, let's start with one of the solved problems. Then we'll go to the fundamental problems and the brainstorming problems based on the concepts we have already discussed in the class. Let's talk about this problem. As far as this problem is concerned, it talks about the simply supported beam. It says the simply supported beam is shown in the figure and is subjected to the concentrated force. Determine the maximum deflection of the beam. EI is constant. Okay. So as far as the beam is concerned, the beam that is given to us is supported at two ends. The beam has support at this end. Okay. That is what we can say. This is the end A, and this is the end C as is already given. Okay, so we are having end A here, and we have end C over here. Fine. Now, in this beam, the total span of the beam is 2 meter plus 1 meter, that is 3 meter. And at a distance of 2 meter from end A, it is subjected to a concentrated load of 6 kilonewton. Okay. Now, first of all, while you are solving the beam deflection problems, what is very important for us is to first do the physical inspection of the beam, understand the physics of the problem. That is, if we look at this overall problem, we know under the influence of the 6 kilonewton load, the beam will deflect, and the deflection curve will have a shape essentially like this. Okay, its shape will be more or less like this. That's what we usually see when we walk on a surface which is supported at two ends. Okay, we have some logs, thin logs of wood. Okay, when we walk over them, they deflect usually like this. They take this type of shape. Okay, as far as the end A is concerned, since end A is fixed at end A, there will be no deflection. That's we write deflection at end A is equal to 0. There is no deflection at end A. We also write that the deflection at end C, that is at this very end, we write this as deflection at end C is also equal to 0. There is no essential deflection. Essentially, there is no deflection at end A and end C. The reason for being no deflection at end A and end C is that the two ends A and C are supported. Okay, they are fixed. Now, these two conditions, that is deflection at end A is equal to 0. There is no deflection at end A, it's a fixed support. And the condition that deflection at end C is also equal to 0. These conditions are essentially known as the boundary conditions. This is what we call as BC. These are the boundary conditions for us. Okay, these boundary conditions we'll be making use of when we'll be solving the beam deflection equations. Now, we know the fundamental equation that we'll be using for solving the beam problem. It is EI. E is the Young's modulus of elasticity. I is the second moment of area about the neutral axis. D2 nu is the deflection. D2 nu by dx2, the second derivative of the deflection equation, is equal to the m of x, that is the bending moment, how the bending moment varies inside the beam. Okay, so in order to find this nu, okay, we should know E, we should know I, we should know the value of m. We should know how this m varies as we move from one end of the beam to another end of this beam. That is, first of all, we should have the what is known as the bending moment equation. So what is important for us is the bending moment equation should be known to us. Okay, so I will write here that known to us should be the bending moment equation. Okay, so first of all, before we use since this is unknown to us, this we have to find. Okay, we'll first of all find the value of m of x, how the bending moment varies inside this beam. If we are able to find the variation of bending moment inside the beam, we can apply this equation to find the value of nu. Okay, so what we will be doing is, if we look at the beam, we have to draw its bending moment diagram, or we have to find the bending moment equation. Okay, since it has a concentrated load, and this concentrated load is acting at a distance 2 meters from the fixed end, we know very well, once we are discussing the concept of plotting the bending moment diagrams, that the point at which the concentrated load is acting, okay, if we have a beam and at the beam we are having a concentrated load, then that beam is to be divided into the left hand section and right hand section. I mean to say that you have to take two sections for finding the bending moment. One section will be on the left hand side of the beam of the concentrated load, and another will be on the right hand side of this this concentrated load. Okay, so first of all, once we are trying to find the bending moment equation, what we will do, let's take a section over here. Okay, let's take a section over here. Let's draw a section here such that this section is at a distance x, or I will say x1, okay, from the fixed end. So once you take this section out, this section will be out as it's like this. Okay, or first of all, let's find the reactions. At this end, at end A, we'll be having reaction upwards, and at end C will be having reaction upwards. Okay, so we know this, let's call this reaction as RA, and let's call this reaction as RC. Now we know from the basic fundamental equations, RA plus RC is equal 6 kilonewton. Okay, this is RA is acting upwards, so we're taking it as positive. RA plus RC minus 6 kilonewton will be equal to 0. That is RA plus RC will be equal to 6 kilonewton. This is when we take the summation of the forces. Then we take summation of all the moments about an axis passing through point A. We write this as summation of all the moments about an axis passing through point A will be equal to moment because of the 6 kilonewton. It will be 6 kilonewton multiplied by its force arm, that is 2 meter, and this is acting clockwise. We'll take it negative. Okay, and we have RC multiplied by its corresponding force arm, that is 3 meter. Okay, should be equal to 0 for the equilibrium. That is 3 times RC becomes equal 12 kilonewton meter. Okay, you have 3 meter, 3 RC meter. So meter will go, RC will become equal 4 kilonewton. So as far as the value of RC is concerned, RC is coming out to be equal 4 kilonewton. Okay, now we have here RA plus RC is equal to 6 kilonewton. Therefore, the value of RA will be 6 minus 4. That is RA will be equal 2 kilonewton. Okay, so we can simply write here. We can therefore write over here that the reaction here is 2 kilonewton, and the reaction over here we have is 4 kilonewton. That's it. Now let's take a section over here such that this section is at a distance x1 from the fixed end. So once we take this section out, we have been stating that at this very end we have to show let the shear force be V. Let's call that as V1, and let's state the bending moment here is M1. Okay, this bending moment we have to find. So again, taking the moments, let's take the moments about an axis passing through the point where we have taken the section. About this axis, we'll take the moments. Okay, so what will happen? The moment M1 is anti-clockwise. This is positive. Okay, and the moment because of 2 kilonewton will be minus 2 kilonewton into axis meter, minus 2x, because it's clockwise. That's equal to 0. Okay, so M1 will be equal 2 times x1. And this is valid when your x1 varies from 0 to 2 meter. That is, this is applicable up to this section of the beam. Okay, the point where you are having a concentrated load and you have to draw the bending moment diagram. What we usually do, we divide the beam into two sections. One section, one bending moment equation we write for the left hand portion, and another bending moment equation we write for the right hand portion. Okay, so here this comes out. So this equation is applicable for this section where our bending moment is M1 is equal to x1. Okay, so this is important. So now what we will do, we'll take one more section, and this section will be taken on the right hand side of this concentrated load, where we say let the shear force be V2, and let's suppose the bending moment here be equal to M2. Take the moments about an axis passing through this point. Okay, where we had drawn the section. So you will be having M2. Okay, M2, and the moment because of this 2 kilonewton load here, that will be this distance we are taking as x2. That will be minus twice x2. Okay, and this distance 6 kilonewton, it is anti-clockwise, plus 6 kilonewton, and its force arm is this much. That will be x2 minus 2 meter. That is x2 minus 2 meter. That's equal 0. Therefore, m2 becomes equal to 2 times x2 minus 6 times x2 minus 2. Okay, so this is the bending moment on the right hand section. That is when your x2 varies from 2 meter. That is, let me clean some space over here. Our x2 varies from here to here. Okay, it goes from 2 meter to 3 meter. That is, we're essentially in this section. Okay, where we have taken m2 to be equal to this, as is also given. Okay, now we will do the separate analysis. Separate analysis means for this first section, we know EI, that is constant, d2 nu by dx2. d2 nu by dx2 is equal to the bending moment in this very section. That is 2 times x1. Since our variable in this section is x1, so in place of x, we have to write x1. That's our variable. So what we will do, we'll have to find the value of nu. Let's integrate it once. Once we perform the first integration, we'll get EI d nu by dx is equal x1 square plus the constant of integration c1. Okay, perform the second integration, we'll get EI nu, okay, is equal x1 cube by 3 plus c1x plus c2. So this equation gives us the equation of the deflection curve. It's a cubic equation, fine. It's a cubic polynomial, but in what section it gives us? As we go from x1, from x is equal to 0 to x is equal 2 meter. Here, the equation will be a cubic equation, fine. Cubical equation, I mean to say. That's how it is going. Okay, this equation is in fact over here. Fine. Now let's go to the next section. Fine. The next section is 2 meter. We'll go from x2 goes from 2 meter to 3 meter. Okay. Write down the equation of the deflection curve. That is EI d2 nu by dx2 is equal to the bending moment equation in that way. That is how much? Since our variable in that very section is in place of x is x2, will be equal 2 times x2 minus 6 times x2 minus 2. So perform the first integration. Once we perform the first integration, it will be EI d nu by dx, EI d nu by dx coming out equal to twice, sorry, 2 will cancel, it will be x2 square minus 3 times x2 square plus twice x2 plus constant of integration. Let's write that constant of integration as c3. Okay, perform one more integration, we'll get it as E1 nu is equal x2 cube by 3. Since we can reduce it over here, you can yes, this will be minus 2 by 3 x2 cube plus x2 square plus c3x plus one more constant of integration, that is c4. Okay, so this equation gives us the equation of the deflection curve for the beam that is from 2 meter to 3 meter over here. Okay. Now let's apply since we are having in both equations, we have C1, C2, C3 and C4. Okay. Let's solve for the C1, C2, C3 and C4. In fact, I will remove it and I will directly go to the equations as given in the books. Okay, so fundamental equations that we have just derived are here as well. Equation of the second, deflection curve, and the first. Okay, this is what we have derived. Okay, now what we do. First of all, let's try to find out the values of the C1, C2, C3, and C4. How do we find the values of the C1, C2, C3, and C4? In order to find the values, what we make use of is what's known as the boundary conditions. Okay, what are the boundary conditions for us? The boundary conditions are, first boundary condition that we have is at x is equal to 0, the value of the deflection is equal to 0. So x is equal to 0 is here. So we'll be making use of this equation. Okay. So once we substitute the value of x1 is equal to 0, this term becomes 0, and left hand side is also 0. So we'll get deflection is 0, that is nu1 is 0 at x is equal to x1 equal to 0 is equal, this term will become 0, this term will become 0. Therefore, our C2 becomes equal to 0. Our C2 is equal to 0. So we don't have to make use of C2 over here. Okay, that's one thing. Number two boundary condition is that at x is equal, x2 is equal to 3 meter. Okay, the value that is here, the value of our deflection is 0 because here the beam does not deflect, it is supported here. Okay, so the value of the deflection nu2 is equal to 0. Why I'm writing here nu2? Because the equation of the deflection curve in this very area, in this region, is represented by nu2. Okay, so I will substitute the value over here. So nu2 is equal to 0 in place of x2. Okay, in place of x2 I have to write 3 meter. Okay, so as to get the value of C3 and C4. Okay, that's quite done. Over here, let me take you to the next page so that it saves some of our time. That's here. That's here. That's what I was talking here. The value of C2 is coming out to be 0. This was at x is equal to x1 is equal to 0. The value of our deflection nu1 is equal to 0. Okay. The second condition is at x is equal to x2 is equal to 3 meter. The value of our deflection nu2 is equal to 0. So once we are substituting in the previous equation, left hand side is 0. This is 4 times 3 by 2 x2 cube. In place of x2 we'll write 3. In place of x2, so we'll get the equation in terms of C3 and C4. That is the second boundary condition that we are writing. Now, what is very, very important for us also, one more boundary condition. So we have got one boundary condition is this, the second boundary condition is this. Okay, since we are having how many variables? We are having C1, C2, C3, C4. We are having 4 variables. So we need essentially the 4 boundary conditions. We need the 4 conditions to find the values of C1, C2, C3, and C4. Now the question is how to do it, how to find the value of C1, C2, C3, and C4. So once we are making use of 2 boundary conditions, we use this boundary condition and this boundary condition, we got C2 equal to 0. And another boundary condition gave us equation in terms of C3 and C4. Okay. So what will happen? So the analysis is now quite easy. What we'll go back to the problem. Okay. Let's return back to the problem to see what else we can use. See, on the left-hand side of this curve, on the left-hand side, that is, I mean to say here, just a minute, over here, okay? The deflection curves is represented by the equation nu1, which is essentially the function of x is equal to x1, okay? Now, from here to here, from 2 meter to 3 meter, it is being represented by nu2 2, which is also the function of x2. Okay, but if you look here, that is at the intersection. Okay, here we cannot have two values of deflection at this very point. There is a question that is quite important for us. That is, at x is equal to 2 meter. What at x is equal to 2 meter? Okay, once we are making use of this equation will give us the equation of deflection curve when x is equal to x1 is equal to 2 meter. And this equation will give us the equation value of the deflection when x2 is equal to 2 meter. Okay, so we are having two equations. This is very, very important. We are having two equations that give us the value of the deflection at x is equal to 2 meter. But the value of the deflection at x is equal to 2 meter given by this equation should be equal to the value of the deflection at x2 is equal to 2 meter given by this equation. Both the two equations should have the same value of equation at x1 equal to x2 equal to 2 meter. Okay, if you do not have the two values of, if the two values of the deflection are not same, say for example, this equation, new one equation says the deflection is, say for example, 1 centimeter. Okay, so it is here. And this equation says, say for example, the deflection is 2 centimeters. So it is here. Okay, so the deflection curve will be somewhat, it will be having discontinuity. That is not possible. Physically, it does not happen, because whatever be the value of the deflection at x is equal to 2 meter, the value of the deflection at x is equal to 2 meter given by the two equations has to be same. Okay, for the continuity of this structure. So we got one more equation, that is nu1 is equal nu2 at x is equal x1 is equal x2 is equal 2 meter. The values of the deflection given by both the sides should be same. Number one. Number two is, deflection curve essentially looks like this. Okay, now if you draw the tangent over here at x is equal to 2 meter, if we draw the tangent to the curve at x is equal to 2 meter, okay, that tangent should have same slope. That tangent should have same, because if this curve, because we are assuming, and what practically is that this curve is a continuous curve. Okay, when this curve is a continuous curve, then at its any point, okay, then at its any point, or at the point where we are having this intersection, where we are having the intersection between the two equations, for the sake of continuity, in order to maintain the continuity concept of this curve, the slope of the curve given by nu1 equation should be equal to the slope at this very point given by the nu2 equation. The two slopes should be same. You cannot have two different slopes at the same point. Okay, so for the continuity at this point, what is very important, that the slopes at given by the equation nu1 should be equal to the slope given by the equation nu2. That is, how do we represent the slope of the curve given by nu1? That is d nu1 by dx1 should be equal d nu2 by dx2. The two slopes should be same. Fine. So we got the conditions. We got now the four conditions. We have constant C1, C2, C3, C4. In order to find the values of four constants, we made use of four conditions. The first condition was at x is equal to x1 equal to 0. The value of our deflection nu1 is equal to 0. This was the first condition. And at x is equal x2 is equal to 3 meter, the value of deflection given by the equation nu2 is equal to 0. Condition 1, condition 2. This is the condition 3, and this is the condition 4. We will be making use of these four conditions to find the value of C1, C2, and C3, as is done over here. So this is the condition 1, this is the condition 2, This is the condition 3. This is the condition 4. So once we are using these 4 conditions, we are getting the values of C1, C2, C3, and C4. All the 4 constants are coming out. So what we have to do, where we have to use these equations, by the way, I will take you back to the previous page. In these equations, that is, in this very equation, you will substitute x1 is equal to 0, nu1 equal to 0. First condition will be subjected, this equation will be subject to the first condition. This equation will be subject to the second condition, x2 is equal to 3 meter, nu2 equal to 0. Okay, this equation, that is d nu1 by dx1 at x1 is equal to 2 meter, is equal to this equation. These 2 equations are same. Okay, when you substitute in place of x2, you will substitute x2 is equal to 2 meter. Okay, fine. Okay, so this is the third condition. And where we'll be applying the fourth condition, that is very important. The fourth condition will be applying in this very equation. That is, in this very equation, we'll say that the value of x1 is equal to 2 meter, and you will get the value of deflection nu1. That should be equal to the value of the deflection given by this equation when you substitute x2 is equal to 2 meters. So in these 4 conditions will be used in these equations. By the way, this equation gives you the deflection. This equation gives you the slope. This is known as the slope equation for this region. This is known as the deflection equation for this region and slope equation for this region. Okay. So once we apply these 4 boundary conditions, what we obtain? We obtain the value of C1, C2, C3, and C4. Okay. So substituting back the value of C1, C2, C3, C4, we'll get the value of. So these are the fundamental equations that are in front of us. Now the question is, where we will the question. So these are the equations of slope and deflection. This is what we had to calculate. Now the question is, where is the maximum deflection? In order to find the maximum deflection, okay, now look, your deflection nu1 is a function of x, okay, and this function v1 will attain the maximum value at which d nu1 by dx1 will be equal to 0. That is, this equation is 0. That is, x1 square minus 8 by 3 is equal to 0. So you can get the value of x1 comes out to be equal to 1.633. So the maximum deflection is at a distance of 1.633 meter. So it is somewhere over here. So we get the maximum deflection somewhere over. Once we move to a distance of, once you go to a distance of 1.63 meter, at that point the deflection will be max. Okay, this is how we have to solve this question. Thank you very much. So in the same way, what we will be doing,